Okay, let's get on with Mr. Khalili, Al-Khalili. We left Mr. Khalili the other day, and again, I'm going to put timestamps on all these, okay? So be aware of that, of you who tuned in late. Here's the summary from last time around. Mr. Al-Khalili essentially said that, they were able to answer all questions with the atoms. Once they figured out the atom, that the atoms actually exist, which is what Democritus said 2,000 plus years ago. Once they proved mathematically or otherwise through experiments or whatever, through deduction, that atoms exist, they were able to answer every question. That's how he starts that's how he boasts, starts his presentation. He says protons are held together by Velcro-like particles, even though there are no Velcro-like particles in the standard model. Okay, sun shines because protons are squeezed together. And what do you mean squeezed? I thought they were being pulled by the Velcro. And see, now they changed the language. They say they're squeezed and squashed from the outside. That's the notion he gives you. So he changes the language and fools you. You shouldn't lose track of the fact that they cannot explain pull. So you should take them back and say, hold it, you just said Velcro. Velcro pulls, two hooks. Please illustrate for me and how that works, that mechanism. I want to see that. And then show that to me on the standard model chart. And of course he can't do that. It's against his religion. Okay, sun can't produce all that helium. He said that's what Gamov suggested, that he couldn't, and it had to be produced at the Big Bang. And later on, they were able to prove the background radiation, the existence of the background radiation, 3 degrees Kelvin there, that was flooding the radars. Okay, and they couldn't get rid of that. Penzias and Wilson, and so they got a Nobel for that, for not being able to get rid of noise. They said, oh, we proved the background radiation, whatever that is. I mean, again, they can't see it. They said we heard it, and it must be there. And where does that come from? Well, that came from the Big Bang 14 billion years ago. And again, it's all this nonsense that they have because it's all done with particles. And of course, with particles, they can't explain anything rationally. And then at the end of the story, they say, well, we don't understand it anyways, but we proved it with experiments and with technology and with math. That's it. That's the answer you get. Okay, so where does he move from there? Well, he justifies how Rutherford, little Ruthy here, and what he did was he was able to show, right, that an atom is mostly empty space. Okay, so he says, concluded that an atom is mostly empty space. The question then became, how could this empty atom possibly make the solid world around us? Yeah, good question. You're saying that all the building that you constructed is all those atoms are mostly empty space? So we have a building constructed out of toothpicks? Is that what these people are saying? Man, don't scare me. Don't tell me that, the Empire State Building, I've been up there, it was made out of toothpicks and almost all completely empty space. Jesus, you should have told me that before I went up there. Okay, so where does he move from there? Well, Rutherford proved that using his gold foil experiment. In other words, he shot some atoms. Okay, he shot them at gold foil, and he was surprised because he thought that all the atoms that made the gold foil surface, that everything would be bouncing back. And actually, all the atoms went through except for 1 out of 8,000. And the one that bounced back, he concluded, hit the center of the atom, which was the proton, the positive proton. That's why it bounced back. That was his conclusion. Of course, he was blind. He wasn't seeing any of this. That's just a conclusion based on what he saw. And again, I don't think Rutherford was a very smart guy. They have him as this hero, like they have all these guys as heroes. And he reached the wrong conclusion because he had the wrong hypothesis. The wrong hypothesis is that everything is mediated by particles. And of course, if you're going to use the particle as your bread and butter, as your building block, then you're going to run into trouble when you try to make sense of it. And that's why they always conclude, well, we don't understand it. Well, if you don't understand it, it means that your conclusion is wrong. You got to go in there and revise what you saw in the lab. Maybe you got to change your hypothesis. Maybe you got to make a new set of assumptions. You never thought of that? No, they just kept rolling with the particles, and they said, oh, the particle bounced back. Well, how do you know it was a particle? Maybe it was, like I said, maybe it's not a bullet that you shot and got back, ricocheted. No, maybe what it was a drill bit. You know, you're with your drill, you're going zzz, and the other drill bit came back out and said zzz. So drill bit is not the same as shooting bullets. Okay, so if we make a new set of assumptions, we end up with different conclusions. That's the point I'm trying to make. Okay, so yeah, for those who hit up on this channel, well, you see a different universe, because we're not talking about bullets, we're talking about drill bits twirling in place. Okay, so it's a different model altogether. Okay, and so continuing with Mr. Rutherford, he said, okay, this is what the atom looks like. Okay, that was his conclusion. He says just a little ball, the electron rolling around the nucleus, in this case the proton. This is the simplest of atoms, the hydrogen atom, right? Okay, but what happened next was that Bohr and Werner Heisenberg, you know, Werner Heise, they came up and they said, look, you cannot even imagine the atom, so don't even try. Whatever you come up with, it's wrong. That was their conclusion after at least 10 years of studying after Rutherford came up with his planetary atom, which Bohr contributed to, by the way, okay, because they were working together. And they concluded that, you know, the atom was first this little electron rolling around the nucleus. They finally gave up on that, at least Bohr did. And he said, look, you know, and Heisenberg, look, you cannot even imagine what we're dealing with here, because it's nothing like you'll see in the real world. And so what does Al-Khalili do? Well, he parrots the party line. This is what he learned by rote in college. Okay, he said the Copenhagen interpretation proposed that the world of the atom ran on principles which were completely different to any that mankind had ever seen before. Okay, I'm not saying that that's not true. Yeah, okay, so it's different. What does that mean? And he said it means that the atom, the basic building block of everything in the universe, was unique and perhaps outside human comprehension. So they were already, putting the fine print, saying, hey, you know, it's beyond human comprehension. Don't try to imagine it, because whatever you come up with, it's wrong. And today we have the same answer. You go to the university and they say, well, you know, that atom that you learned in high school, you know, the little planetary atom, that's okay for babies, you know, kindergartners, that's there. When you come here, we've got a better atom. It's the one you can't imagine. That's what you get. That's what you get in college. So if you want to miss 10, you don't want to lose 10 years going to college, I'll tell you right up front. The one you learn in college is that you cannot imagine it. Okay, so let's get that straight right up front. They'll all tell you that. Okay, so here we have the atom that you're not supposed to imagine, which are nucleus made of these little balls there, supposedly protons and neutrons, and you have the little whatevers, little beads just floating around and buzzing around like bees on a beehive. Okay. And yeah, so we have a problem here, because this is my version of their atom. If their atom is a proton and an electron, what prevents them from illustrating that proton and an electron? Here you have it. That's the hydrogen atom. What's so difficult about this? I mean, that's what they show on the chart, on the standard model chart. They don't show the proton these days. They show it as 3 quarks. Fine, you can put 3 quarks inside that proton if you want. And then you have the electron next to it. That's a snapshot of the atom when it's not moving. Okay? When it's standing still. It's the only object in the universe, even though there's 2 objects there, the electron and the proton. If that's their atom, there it is. You know, what's so difficult about it? Why can't you imagine this pair here? And yeah, the reason you can't imagine, the reason that's not true, that's not the actual atom, is that an atom behaves in such a way that denies that that's the atom. They use that atom anyways. They use the planetary atom to explain ionization. They use it to explain electricity. You know, the little bead going from atom to atom. They have no problem there. They invoke that planetary atom. When you say, well, is that the atom really? Well, no, it ain't. Well, if it ain't, then why did you use that as a model? If it ain't, show me the real model. And of course, they can't put the real model. They use that model always to explain electricity, and then they deny that that's what it is. They say, well, that's just an analogy. Don't take it seriously. And you say, well, but you just explained how the electron moves from atom to atom. So I guess what you're saying is that electron is a little bead going from bowling ball to bowling ball. That's your explanation for electricity. Ionization along the same lines, the electron just leaves the atom, right? Or another electron comes in case of negative ions. That's what you just explained. So you're saying that's your atom? How can you later on deny and say, well, that's not my atom? Then your whole presentation was garbage. That's what you're telling me. Because that's the atom you use to explain electricity. Are we understanding ourselves or not? We got a problem because they point to this atom, to this atom, right? The Bill Gates model of the quantum hydrogen atom. And then they say, yeah, that's what we're going to use to explain electricity, but then don't take it seriously because that's not our atom. Okay, so we got a problem. We got a problem because these people cannot explain any phenomenon in the invisible world of the small. And then they claim they proved it, that computers wouldn't work if quantum were incorrect. So what are they talking about? We got a problem because they can't imagine their atom, but they say they proved it. They say they cannot explain, but they know exactly what their atom looks like. It looks like a planetary atom. We got a problem, folks. Forget it. No matter how you twist and turn this, we got a problem. Okay, so here's Atom Man Al-Khalili, and he says, as scientists explored the nucleus, they found it bursting with powerful energy. Yeah, they started to what they claim is split the atom. I'm saying they split their heads, they never split the atom. There's another mechanism to explain, atomic behavior or fission, okay? But they thought they split the atom, that they parted the atom in half, like parting your heart in half or something. Okay, this discovery gave them a fundamental understanding of how the universe itself was created. My God, they took this a step further, and now they can tell you through the atom, okay, they can tell you how the universe came into being, meaning how matter came into being, okay? Because here you have this burst of energy coming out of such a small thing. Once you parted the seas right there, so to speak, you parted the atom. Okay, you have all this energy. Now we know how the universe came to be. There was a big explosion. All this energy was released, and that energy, a concept, right, turned into matter. Because Einstein already showed that energy is equal to mass times velocity of light squared. And what is mass? Matter. In the jargon of mathematical physics. So you got to replace that word mass with the word matter, and you'll be okay. You'll understand perfectly. In other words, energy turned into length, width, and height. It acquired length, width, and height and turned into matter known as mass, known as weight. Okay, that's essentially, the theory. Okay, so what are the problems? And the problem comes from Al-Khalili himself. He said, I'm not saying this, that's him saying this, okay? By the late 1920s, the equations of quantum mechanics were consistently getting the wrong answers when describing electrons, okay? We're talking about 1929, etc., okay? What is it, the roaring 20s, okay? Just before the stock market crash. The constituents of atoms as they moved at very high speed. So now they could not explain the behavior of electrons moving at high speeds. What were they trying to analyze here? They were trying to analyze special relativity. Okay, because they were trying to incorporate special relativity, the conclusions of special relativity. In other words, moving at the speed of light or close to the speed of light, what would happen to objects? You know, you get legs contraction, mass increase, you get all this nonsense out there. And they said, well, how do we incorporate this into quantum? Because now here we're shooting electrons at very high speeds. And so how do we explain the behavior? It doesn't match. They couldn't merge the equations of quantum mechanics with those of special relativity, especially, or you can even say general relativity, relativity in general. Okay, so where do we go from here? Okay, and well, what happened was instead of fixing the problem, they just made it worse. They brought in good old Paul Dirac, and what he came up with is his equation, the Dirac equation, having to do a little bit with the Dirac sea of all these particles floating out there, making up space, coming in from the void. You have matter and antimatter joining hands and turning into space, and then splitting apart and forming very brief particles that come into our world just to make the mathematical equations come out right. You know what I mean? Okay. As well as matter, Dirac's equation predicts the existence of antimatter. Okay, that's what that equation does. Okay, for every particle there can exist an antiparticle. Okay, this opened a can of worms because the first problem was that it was confirmed, as you know, all these things are usually confirmed through experiment. And so what was the issue? The issue is that good old Dirac predicted one thing, that, and this is very important, okay, that if you get matter and antimatter together, there's a big kaboom, big explosion, big no, you don't want to do that ever, okay? And he says, and there's one final prediction of the Dirac equation. As its punchline, it states that matter and antimatter must never come into contact. Because if they do, they will annihilate each other in a fierce conflagration of pure energy. Okay, whatever that is, okay? Energy, a concept, so they end up being a concept. The combined mass of matter and antimatter would convert completely into energy, to a concept, according to Einstein's famous equation, blah, 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 okay? If I ever do meet my doppelganger, we would explode with an energy equivalent to 1,000,000 Hiroshima-sized atom bombs. Okay, you understood that, okay? You got matter and antimatter. If they come together, you get nuclear explosions, nuclear level explosions. We got that straight? Okay, let's find out what the problem with that is. Okay, here goes, okay? Now go get your beer, because you're going to need a beer for this to understand this. Here it is, okay? According to good old Al-Khalili, says antimatter, particularly antimatter electrons called positons, are made routinely now in laboratories. They make them in labs every day. The CERN, Fermi Lab, SLAC, stands for Linear Accelerator. They make antiparticles every second. That's what all these people do. They just shoot whatever this invisible stuff. They create antimatter, and then the antimatter immediately recombines with its matter. And as far as I know, we don't see all these explosions all around us. He just said that if matter meets antimatter, we get this big boom, this kaboom. And he says we make it every day in the labs. I hope you make sense of it, because I can't. Positrons are used in sophisticated medical imaging devices called PET scanners that can see through our skulls and accurately map pictures of our brains. They're throwing these positrons, these antimatter particles, into your brain. Maybe that's what's causing your dementia. Yeah, we got a problem with all these bozos because they're contradicting themselves. On the one hand, they tell you, look, if matter and antimatter come together, big kaboom, nuclear explosion. And then they say, oh, it's happening all around us. All these antiparticles and particles are coming in from the void and then recombining it, releasing a whole bunch of energy. So we got all this energy just exploding in front of our eyes. I wonder why we don't notice it, because if it's like nuclear explosions, you would think that you would at least notice it, maybe even hear it, you know. Absolute nonsense. Well, okay, a few years later, this fellow here, Carl Anderson, supposedly he discovered what I call the sup-positron. He supposed that that line that you see, that curved line, the big one right there almost in the center, he said, look, that's an antiparticle because, or antimatter, because it's moving in the wrong direction. It's moving negatively, I'm sorry, positively when the electron, if it were an electron, it would be moving in the other direction, it would be moving positively. So he supposedly discovered the positron, and for this sup-positron, the discovery, he got the Nobel Prize in 1936. So this is not trivial matter, okay? Now, in science, Mother Nature, she doesn't know what positive or negative or North Pole or South Pole are. All she knows is what clockwise and counterclockwise are, okay? So if this is a counterclockwise and the electron would do a clockwise, all we have is something that these people don't understand, which is that curve there is only a counterclockwise curve. That's all it is. No positive, negative, no North Pole or South Pole. It's just clockwise and counterclockwise. Period. We're done. That's physics. That's not math. What this guy did was math. Okay, again, these guys were not bright, not one of them. They should all return their Nobel Prizes because they're worthless anyways. They're just tin, pieces of tin that they give out. Okay, of course you can buy a lot of beer with the prize, but you know, these people just give prizes to each other. That's all they're doing. Then the guy who receives a prize then becomes to, you know, he's one of the guys who can designate who the next Nobel is. So it's a self-perpetuating system. That's why quantum is still around today, because all these guys just give pats in the back to those people who follow them right after them, you know, from the next generation. So it's a self-serving, self-perpetuating system that we've created. We humans, smart humans, right? All we did was continue to paint ourselves into a wall. Okay, so here you have the Dirac equation, and it says describe one electron. It failed to explain behavior when there was more than one electron present. That was the shortcoming of Dirac's equation. How do you deal with electron to electron interaction? And wouldn't you know it, they always have a solution. And the solution came from a fellow by the name of Richard Feynman. What was it? I think 1948. And he invented this nonsense, the so-called quantum electrodynamics. Okay, and he came up with these so-called Feynman diagrams. And you see that little squiggly line. And what are we seeing there? Well, you see a positive electron and a negative electron. And they shoot out this little thing. That's how this little squiggly line, whatever that is, I guess it's a wave, you could say, or maybe it's a particle going up and down. I don't know how you're supposed to interpret that picture. The funny part is that Niels Bohr, who heard his presentation, and Paul Dirac and all these other fellows from the old days, Heisenberg, they called him an idiot. Yeah, they called Richard Feynman an idiot. That's what Al-Khalili says. They called him an idiot because he was trying to make a picture of what was happening, and they said, you're crazy. You cannot even imagine what's happening out there in this invisible world of atoms. And this guy was drawing it. Now, how was that for overthrowing the old regime, okay, the old guard? So they were absolutely pissed at him. But what happens is the old guard died, and the new guys, you know, like Schwinger and him, who got the Nobel Prize for this nonsense, they took over, and they overthrew the old people, okay? And they started making pictures of the atom back again, okay? One of the guys who participated in that was, well, hold it, here's one step here in between. Al-Khalili is shocked because Feynman says that he cannot even imagine his own theory. Says, so what does QED actually say? It may be a wonderful scientific description of nature, but trying to understand what Richard Feynman was doing with his theory is almost impossible. No, not almost. It is impossible. This is what he himself said when he introduced his theory to the public. It is my task to convince you, not to turn away because you don't understand it. Okay? You see, my physics students don't understand it. That's because I don't understand it. Nobody does. So Al-Khalili makes this comment. He says, if the inventor of the theory doesn't understand, what possible hope is there for the rest of us? Yeah, what possible hope is there if no one understands, as Feynman says, and certainly Bohr and Heisenberg and Dirac, who were at the meeting, they said, we don't understand it. And he said, yeah, you're not supposed to understand it. You're just supposed to visualize it the way I'm putting it here in little pictures on the board. And so they were upset. They said, you're trying to draw the atom. You're trying to draw the behavior of the atom. You're trying to illustrate electron to positron interaction. And he said, yeah, but see, it's just a kindergarten thing just to visualize. No. Don't try to cheat. You can't cheat. You can't visualize it. Do you understand? You're an idiot. And so the idiots took over and they overthrew the old guard. And here we have, if I can get this thing up here. So many of these. So what does Al-Khalili say? Well, he says, even though no one can understand it, he's going to try anyways. Okay, you're supposed to try to listen, follow his steps. Okay, he can visualize it for you, so please try to understand. But he starts out on the wrong foot. Okay, he says, with that disclaimer, I'm going to try to explain anyways. Okay, first you have to abandon your most basic intuition about nature. Oh man, that's a bad way to start a presentation where you're trying to explain to someone who you want to understand your theory. He said you're supposed to abandon your intuition. Leave all rationality behind. Okay, I'll do that. You have to give up the notion that empty space is empty. Okay, so that's how he starts. And then he says, quantum electron dynamics says that the vacuum is not the place where nothing exists and nothing happens. Instead, it's full of stuff and it's heaving with activity. And there you have it. That's the quantum vacuum. Just a bunch of particles made of, what is it? What did Paul Dirac say? Matter and antimatter that just keep recombining, known as annihilation, and then coming back into our world whenever the mathematician needs to explain something. So he brings these particles in momentarily because I don't understand what the purpose of these particles is. If the particles just come in and then immediately, because he says they last a very, very short time, picosecond or even less, in our world then go back, then what's the purpose of these virtual particles? Well, no, that's the explanation he gives you, but then the mathematicians bring them in and they do a lot of stuff with these virtual particles for hours and hours. So the virtual particles running around, they explained a lot of stuff with that, and say, okay, now we're done with a virtual particle, you can go back, be in space again, go recombine. And do your boom and do that nuclear explosion. Just don't blow me away. We got a problem with the mechanisms. Of course no one understands this because they don't make it understandable. Okay, but if you thought that irrationality stopped there, no, then we have this fellow. His name is Murray Gell-Mann. And he came up with a 3-quark deal. He got a Nobel for this nonsense, saying that, yeah, we have these 3 quarks. They make up protons and they also make up neutrons. And of course, they fit in the gluon in there to keep track of the standard model, which was becoming what they called a particle zoo. Everybody was getting a Nobel Prize for discovering a new particle every day. And so that's why we ended up with so many particles. The main ones are like 12. There's a couple more, like the graviton is not part of the standard model. But they have a total of like 200 particles. You have phonons, the particles of sound. You have tachyons, particles go faster than light. You have, what's the other one, famous one? The chronons, particles of time. And then you have the particles of mass, of weight. You have the Higgs. So they have all these particles, out there. They got like 200 particles sub-particles that they created, muons, pions, the whole works. You got a bunch of particles out there. And so the question is, what does this lead to? Well, first let's summarize what Al-Khalili said essentially. Okay, here it is. Give me a second here, okay? The mechanics started out by claiming they proved the existence of the atom. That was at the early 20th century. From there, they figured out that the atom was mostly empty space. Then they figure out that empty space is not empty. You know, they have all these matter and antimatter particles out there that make up space. You know, like I say, a black ball and a white ball, they get together and form a no ball. Yeah, they have no balls in quantum, okay, and quantum empty space. Empty space is full of these particles doing a lot of activity out there, so they are particles, okay? Dirac invents antimatter, that's part of that deal. Anderson confirms it, okay? If matter and antimatter collide, you have a nuclear explosion. However, the mechanics claim they produce antimatter every day in the lab, okay? So we have a problem there. Okay, and Feynman invents QED with his little kindergartenish diagrams that offended all the old guard. Okay, he did it to solve Dirac's inability to deal with two electron interactions. Okay, and then Gell-Mann invents three quark to make protons and neutrons. So that's the model. That's the vision you're supposed to have of the atom today, of the quantum atom, whatever that means to you, whatever vision you have of that, because once you get that vision, they say, forget it, you're not supposed to imagine it anyways, you can't imagine it, okay? It's just used for visualization. So you ask, well, what's the state of the art physics today? Where has all this taken us, okay? What's the conclusion? What's the corollary to all this? And yeah, here it goes. Again, get a beer. You're going to need it. Okay. Here it is. Bohr and his generation overthrew the old order of classical mechanics. Okay. The people who died at the end of the 19th century, including Einstein, those people, they were left behind. They said, you guys don't know anything. You know, we've got a new model, and it's this quantum model, which Einstein at least didn't believe in. A lot of the old folks didn't. I know this... Michelson from Michelson and Morley experiment, he didn't believe in the quantum model. Even, what was the name? Max Planck, he didn't believe in this quantum nonsense. Okay, he tolerated it and saying, well, this is a new generation, but he didn't believe in it. De Broglie and Schrodinger, they overthrew Bohr's little particles, you know, quantum jump and so on. They said, no, it's a wave and it's cloud. And then Dirac comes in there and Anderson confirms it. And they said, no, look, forget about your waves. It's particles, because we have all these particles and antiparticles, matter and antimatter out there, and they form not only the background, the empty space, but they also form the atoms. Okay, and that was confirmed later on by putting the quarks that Gell-Mann came up with. Feynman overthrew Heisenberg's notion that the atom cannot be visualized. And what happened in the end? Well, string theory overthrew them all, because nobody does quantum mechanics anymore today. It's all string theory. That's where we're moving into. Every student of so-called physics, mathematical physics, they're abandoning quantum mechanics, because quantum mechanics has no solution to quantum gravity. And so quantum gravity is a buzzword for string theory. And they're going into this math. They're not going into physics. They're not trying to visualize any of this. They're going into string theory, which is math. They're trying to get an equation that unites quantum with gravity, quantum with relativity. And of course, they have a big problem there, because again, relativity is warp space and quantum is force. And we got a problem there, because you know, two different mechanisms. How they're going to get the equations together, well, only God knows, you know. Corollary, we have no use for accelerators, because if quantum is dead, essentially, right, other than for dark matter, which they're trying to, that's the new jobs of the people working at the accelerators. They're into dark matter, okay, and dark energy, because forget about the atom. That's already complete. You know, they can't do anything more with that. That's where the string theory is to worry about, you know, the vibrating line. Okay, and meanwhile, these guys say, what do we do? Well, why don't you guys work on accelerating stuff in there and try to produce dark matter? Okay, which is what we need to figure out, how what's happening out there in the galaxies. Okay, so the issue is that essentially they have no use for these white elephants like CERN and SLAC and Fermilab. No use for them anymore. It's like, you know, just look busy. That's it. So if you work there, just look busy. You got a high level job, you get paid, You were recommended by your advisor, physics advisor or PhD advisor. You're done. You got a career. Forget about trying to make sense of any of it. And these are the people who are followed by millions of people who say, oh, these guys know because otherwise we wouldn't have computers and GPS and so on and so forth. That's the state of humanity today. Okay, that's where we arrived.